Welcome to the Deep Dive, where we take complex technical documents and, well, we give you the essential digestible roadmap so you can become immediately well-informed. Today, we are tearing into the world of AI algorithms, and we're moving far beyond just thinking about simple customer service chatbots.
Right.
We're really exploring how artificial intelligence is, revolutionizing the deepest foundational pillars of business, specifically customer relationship management, or CRM, and of course, customer experience, CX.
And our mission today is, I think, a really crucial one for anyone who's navigating the digital economy.
Definitely.
It doesn't matter if you're running a massive e-commerce operation or, managing just a handful of massive B2B accounts.
Right.
You need a clear, thorough shortcut to understanding all the complex technical jargon that surrounds true personalization, prediction, and automation.
And we have the source for that.
We do. We're diving into a really comprehensive technical white paper that lays out the exact algorithms that are fueling this massive shift.
And the simple truth is, what? That the old systems just can't keep up.
The simple truth is that traditional CRM systems are paralyzed. They're paralyzed by the sheer volume, the velocity, and the complexity of modern customer data. We're talking everything from social media sentiment to, connected device telemetry.
Wow.
AI is no longer a strategic choice. It's the essential tool for delivering an exceptional experience, whether you're dealing with millions of B2C transactions, these intricate B2B engagements, or even managing multi-layered channel and dealer networks.
That sets the stage perfectly. So we're talking about moving from basic data, storage, to something much more active.
To proactive, intelligent, and seamless customer interaction.
Okay. So the systems are essentially learning to predict your needs before you even know them yourself.
That's the goal.
Okay, let's unpack this, starting with the fundamental non-negotiable concepts that form, the architectural basis of any truly AI-driven CRM or CX strategy.
Exactly. When we talk about integrating AI into customer strategy, we always start by building the structure that's necessary to handle all that diverse data.
Makes sense.
We need three foundational pillars that organize the data, automate the expert insights, and ensure we capture the holistic customer story.
And the first one is called knowledge data representation. It sounds incredibly formal, I have to say.
It does, but you can think of it as the brain surgery required to turn messy, chaotic data into actionable intelligence.
Okay, brain surgery. I like that. So it's the architectural blueprint.
It is the architectural blueprint of your intelligence layer. Knowledge data representation involves creating these highly structured, formalized databases that store essential customer information.
And like you said, this goes way beyond just a simple list of past purchases, right?
Oh, far beyond. This structure includes detailed customer preferences, comprehensive purchase histories, granular product catalogs, service incident records, and the core business rules that govern all the interactions and incentives.
So the data isn't just sitting there.
No, it's organized to be instantly readable by a machine learning model.
So the key value here then is instantaneous relevance.
Exactly.
Instead of a human agent or even a legacy CRM having to hunt through all these different siloed systems for information, the AI layer just makes sure the customer-facing teams have the most relevant current info immediately, right at the point of interaction.
It shrinks the time to insight. That's the perfect way to put it.
Okay, so give us an example. B2C.
Okay, take B2C. By organizing customer preferences, their preferred color, size, maybe brands they browse but don't buy, or even the time of day they're most likely to open an email.
That's specific.
That's specific.
Yeah.
That knowledge representation foundation allows an online retailer to offer perfectly tailored product recommendations and promotions.
I see.
If you know a customer is an early adopter, but maybe they're sensitive to price increases, you can target them with a discount code for a new product. That increases conversion rates because the offer feels, deeply specific and valuable to them.
But this isn't just about high-volume retail. You mentioned this is arguably more critical in the complex B2B landscape?
It is, absolutely, because B2B relationships are long-term and they're multifaceted.
Right.
For B2B and key account management, knowledge representation stores this detailed, longitudinal information about the entire account.
So not just one person, the whole company.
The whole company. It often includes complex contracts, highly technical specifications, and purchase histories spanning years across multiple business units.
And that structure allows the sales team to do what exactly?
Well, it allows them to provide highly strategic and personalized recommendations. For example, they can anticipate necessary equipment upgrades or proactively suggest cost-saving solutions based on predictive modeling of the client's own industry trends.
So it transforms the sales team from just order takers into
Strategic advisors.
strategic advisors. Okay. And what about managing channels, like a network of independent dealers or service providers?
A well-structured knowledge database lets businesses manage and store highly standardized information on dealer performance, their training status, customer interactions, across all those multiple channels.
So consistency.
It ensures every customer gets a consistent experience no matter which dealer or service channel they happen to interact with.
Okay.
If a customer has a complex piece of machinery, the knowledge base makes sure the local dealer has access to the most recent troubleshooting protocols instantly. This optimizes the overall channel strategy and, it builds trust.
Okay, so moving on. Once we have that strong foundation, that knowledge representation, the next pillar starts to generate actionable guidance based on that data. We're talking about recommendation expert systems.
Right. These systems take expert knowledge, so rules based on historical success, and they combine it with automation to assist the human element.
Whether that's a sales rep, a service agent,
Or even the customer directly. They don't just pull raw data, they interpret it and suggest precise next steps.
So the real-life application, and I'm guessing the one that saves the most time, is in customer support.
That's a huge one.
When a customer contacts support, the system doesn't just show the agent the customer's history.
Yeah.
It actively suggests immediate, precise troubleshooting steps.
And they're tailored exactly to that customer's specific product configuration, their past issues, and maybe even their current behavior captured by IoT sensors.
So the key benefit is efficiency through context.
Exactly. By automating the routine diagnosis and using this integrated expert knowledge, businesses can streamline interactions and ensure consistency. In B2C, this drastically reduces resolution times and improves customer satisfaction dramatically.
And in B2B, the strategic impact must be enormous.
It's huge. If a large account faces a recurring, complex technical issue, the expert system can suggest customized solutions drawn not just from their own history,
But from everyone else's.
but from industry best practices gleaned across hundreds of similar high-value clients globally. This personalized strategic approach strengthens that key account relationship because the client sees the business operating as a highly intelligent, unified entity.
And I can see how this extends to the channel partners, too.
It definitely does. The system can provide dealers with tailored recommendations for, say, product configurations or specific sales strategies based on local market data and customer profiles.
So if a dealer runs into a problem,
If a dealer encounters a specific product query, the system suggests the best solutions and potential upsell opportunities based on the customer's profile and the success rates of similar historical interactions. This elevates dealer performance and ensures the customer experience stays high quality no matter where it happens.
okay, so we've structured the data and we've built the expert guidance. Here's where it gets really interesting because now we're moving beyond just text or, structured databases. The third foundational concept is multimodal AI. And this provides a truly comprehensive, a holistic approach to understanding customers by integrating all these diverse data types.
Right. Multimodal AI is necessary because humans, we communicate in more ways than just typing.
Right.
This approach combines natural language processing, or NLP, with image, video, and audio analysis. The goal is to gain deeper, more nuanced insights by analyzing every form of customer interaction simultaneously.
Okay, let's break down those modalities, starting with the one that drives most communication, NLP.
NLP is pivotal. It's for analyzing text-based interactions like emails, chat messages, social media posts, survey comments.
All of it.
All of it. It has several crucial functions: detecting sentiment with high accuracy, extracting key entities and information like product names or complaint specifics, and then providing automated responses or intelligent routing.
So it can sort the mail, basically.
A robust system using advanced NLP can instantly categorize an incoming customer email. Is it a billing issue, a technical support request, or a compliment? And it routes it to the specific agent or automation stream best equipped to handle it. That dramatically increases response agility.
But the truly multimodal aspect brings in the visual. And that's becoming more and more common when customers are trying to report, say, damage or defects.
Yes. For visual data, we rely on image and video analysis. This interprets visual information shared by customers or captured during interactions.
I can just send a picture of my broken thing.
Exactly. A customer can send a photo of a cracked part, and the AI, using specific image recognition models like convolutional neural networks, can instantly identify the exact model number, assess the severity of the defect, and automatically initiate the correct return or replacement process.
Wow. And video.
Furthermore, video analysis can be used, with consent of course, to evaluate the interactions that happen during a video support call. It can provide real-time feedback on agent soft skills or detect moments of customer frustration through nonverbal cues.
And then there is audio analysis for voice data, which is more than just transcription, I'm guessing.
Oh, absolutely. Audio analysis transcribes and then it analyzes the underlying voice data from calls or messages.
What's it looking for?
The AI detects the sentiment changes: stress, anger, relief. It recognizes crucial keywords, and it gauges the urgency of the issue. A common use case is real-time call center routing.
Okay.
If the audio analysis detects high emotional stress and keywords related to a severe outage, the system overrides normal routing and sends that call instantly to a Tier 3 specialist.
So it ensures high-priority issues are addressed promptly and, I guess, handled with the right level of empathy.
Exactly. It ensures consistent, empathetic handling across the entire service team.
So if we connect this multimodal approach back to the bigger picture in B2B, how does this level of data complexity benefit those high-stakes key accounts?
It provides the most comprehensive strategic support possible. Imagine a B2B key account manager preparing for a quarterly review. The system analyzes detailed email exchanges using NLP. It extracts core commitments and strategic decisions from meeting transcripts using audio NLP, and it can even integrate visual logs of product usage data.
So you get the full picture.
Integrating all these data types gives a much richer 360-degree understanding of the client's current operational health and future strategic needs. It allows the manager to walk into that meeting with unparalleled, proactive, and personalized recommendations.
That's a really robust framework for handling and understanding customer interactions. Now that we understand what kind of data AI uses and where it's applied, we have to talk about the core machine learning division that dictates how the AI actually learns. Supervised versus unsupervised learning. This is the essential first step in knowing which tool is right for which job.
This truly is the fundamental difference in machine learning strategy. It all boils down to the nature of the training data you feed the algorithm and the specific prediction or discovery goal you're trying to achieve.
Let's start with supervised learning. The core concept here, it revolves around labeled data, which it sounds a lot like teaching a child with flashcards.
That's the perfect analogy. Supervised learning algorithms are trained on data where the input has a corresponding known output. The data is labeled.
Okay.
You show the model 1,000 pictures of dogs labeled dog and 1,000 pictures of cats labeled cat. The model's sole purpose is to learn the mapping function so that when you show it a new unseen picture, it can accurately predict the correct output label.
So the key challenge, and I guess the necessary upfront investment, is data quality, right? If the data is mislabeled, the model learns the wrong lesson.
Exactly. The accuracy of the supervised model is entirely dependent on the quality and the fidelity of that initial labeled data set. If your historical data is poorly categorized, your future predictions will be unreliable.
And in the CRM/CX world, we use supervised learning for what?
We use it explicitly for predicting outcomes we already understand.
What are some of the most critical applications based on our source material?
The primary use cases really center on classification and prediction tasks.
Okay, let's start with the financial and retention side. Customer churn prediction.
This is a classic example. You use historical customer data spanning behavior, demographics, service interactions, and you label it explicitly as churned or retained after a certain period.
Right.
The resulting model can then predict the likelihood of a current customer leaving. It often assigns a probability score like, this customer has a 78% likelihood of churning.
And that lets companies proactively intervene with retention campaigns before the customer actually leaves.
Exactly.
And as we touched on earlier, we use it constantly for immediate sorting and organizing, which speeds up response times.
That's email and chat classification. Raw customer inquiries are labeled by human agents or automated processes: technical support, billing, product inquiry, and so on.
And the model learns to do that sorting automatically.
The supervised model learns to instantly and automatically route new, unlabeled inquiries to the appropriate specialized team. That minimizes transfer time and frustration for the customer.
We also use it constantly for gauging customer emotion.
Right. Sentiment analysis, feedback, reviews, social media posts are labeled with sentiment scores, positive, negative, neutral, or even more nuanced labels like frustrated or satisfied.
And then the model can predict the sentiment of new interactions.
which is vital for instantly gauging satisfaction, escalating negative interactions, and identifying emerging product or service issues in real time.
And finally, the essential forward-looking financial applications.
That's sales forecasting. By training on historical sales figures labeled with corresponding market conditions, seasonality, and other relevant customer attributes, the supervised model can predict future sales numbers.
Which helps with inventory, resource allocation, cash flow.
All of it. It allows businesses to fine-tune everything.
Now, let's flip the coin to unsupervised learning. This is a completely different approach because now we are dealing with unlabeled data. We're going in kind of blind.
This is the discovery phase. The model is trained on raw data where there are no predefined labels or outputs.
So the goal isn't to predict a specific answer.
No, the goal is to identify hidden patterns, intrinsic structures, or inherent relationships within the data itself. It's like being given a massive box of mixed-up customer behavior records and being asked, what groups naturally exist here?
So instead of predicting a known outcome, we're discovering previously unknown useful structures that can then inform our strategy.
Precisely.
What are the key CRM CX use cases here?
Well, the classic and most fundamental example is customer segmentation, which we often refer to as clustering.
How does that work in practice to, say, inform marketing?
The algorithm analyzes raw customer data demographics, purchase history, engagement patterns, website visits, and it groups them into segments or clusters that share common characteristics.
So it might find...
It might identify a segment of high-value weekend shoppers or budget-conscious, infrequent buyers. This foundational machine-discovered segmentation is far more granular than what a human could achieve, and it allows for highly precise, targeted marketing campaigns.
It's also instrumental in spotting fraud or system anomalies, right?
That's anomaly detection. The algorithm learns what normal behavior looks like for a customer or for a system.
And anything outside of normal gets flagged.
Any data point that deviates significantly from that established normal pattern, sudden, unusual changes in purchasing volume, odd login locations, suspicious account activities, is flagged as an anomaly. This is crucial for detecting potential fraud, high-risk customers, or even identifying failed system deployments.
And for recommending products in a way that feels organic and sometimes surprising.
Product recommendation uses unsupervised learning to identify those intrinsic relationships between products that are purchased together. This is the engine behind cross-selling and upselling opportunities.
And it can find non-intuitive connections.
That's where the surprising insight often emerges. The model might find a really non-intuitive correlation, for example, between the purchase of advanced power tools and gourmet coffee. This insight allows the retailer to place those seemingly unrelated items in front of the right consumer.
And finally, for understanding broad, unstructured feedback trends.
Voice of the customer analysis. When customers provide raw, unstructured feedback, like in open-ended survey responses or massive volumes of social media comments, unsupervised learning identifies common themes, recurring keywords, and collective pain points automatically.
So it saves a human from having to read every single comment.
It pulls out the essential structure, providing actionable insights for service improvement and product development without all that manual effort.
Okay, so to summarize, supervised learning is about predicting known outcomes based on history and high-quality labeled data, while unsupervised learning is about discovering hidden, valuable structure in the raw data. With that framework in mind, we can now step into the algorithm toolbox itself. This is where we name names and see exactly how these mathematical tools execute those predictions and discoveries.
This is where we get specific. We'll explore the key algorithms mentioned in the source material, starting with the supervised models used for prediction and classification, and then we'll introduce the deep learning models that are necessary to handle today's complex, unstructured data.
We'll begin with the most basic and often most useful predictive model, linear regression.
Linear regression is fundamental. It models the linear relationship between a dependent variable, that's what you want to predict, and one or more independent variables, which are the inputs.
So in CRM, this is for predicting continuous values.
Right. For instance, you could model the relationship between the time a sales rep spends on a lead, that's the input, and the resulting size of the sale, the output. The model establishes that correlation to forecast sales figures.
Simple and explainable.
Very. But it does struggle with complex, non-linear relationships.
Okay, so stepping up the complexity slightly, we move to classification with logistic regression.
Logistic regression is specifically designed for binary classification predicting yes, no, 0, 1, or true-false outcomes.
even though it has regression in the name.
Right. Its core function in AI is classification based on probability. A perfect case use is predicting customer churn.
How does that work?
The model uses factors like the number of support tickets a customer has opened, their contract length, and their engagement score to calculate the probability of them churning. If that probability crosses a predefined business threshold, the output is a clear classification. Yes, this customer is highly likely to churn. Engage the retention team now.
Next up, we have decision trees, which are highly intuitive and, I'm told, easy for humans to interpret.
They are. Decision trees are essentially AI-driven flowcharts. They split the data at each step based on the feature that provides the most informative distinction, continuously branching until a prediction or classification is reached.
Can you give me an example?
Sure. Imagine you're predicting if a customer will buy a luxury car. The first split might be income is greater than 150K. If yes, the next split might be owns a home. The tree visually represents that logic.
And a classic use case.
Predicting churn in a high-volume service provider context. By segmenting customers based on simple, informative features like tenure, contract type, and recent billing complaints, the decision tree can isolate at-risk segments quickly, allowing for highly targeted, proactive retention.
Okay, for classification that requires drawing clean lines and highly complex multidimensional data, we use support vector machines or SVM.
SVMs are incredibly powerful for classification. They work by finding the optimal boundary, or what's called a hyperplane, that separates different data classes in a high-dimensional space.
So it's not just simple splits like a decision tree.
No, the SVM finds the single best line that maximizes the margin between the two groups. In an e-commerce context, FVMs are used for sophisticated product recommendation by classifying new items based on similarity to past purchases, looking at category, brand, color, material, and price to ensure highly relevant suggestions.
When we need to boost accuracy and reduce the risks that come with relying on the errors of a single model, we move to what are called ensemble methods, starting with the random forest.
Random forest is a major step up in reliability. It's an ensemble method that builds many independent decision trees, hundreds, sometimes thousands, all trained on random subsets of the data.
So it's like asking a committee of experts.
That's a great way to think about it. When a new data point comes in, it's run through all the trees, and the final prediction is based on the majority vote. This averaging process significantly improves accuracy and reduces what we call overfitting.
And it's used for?
It's frequently used in marketing to predict customer churn probability or lead conversion scores, making targeted retention and sales campaigns much more efficient and reliable.
And the most sophisticated and often most accurate ensemble technique for prediction is gradient boosting.
Gradient boosting is structurally different from random forest. Instead of building trees independently, it builds them sequentially.
How does that help?
Each new decision tree focuses specifically on correcting the errors and residuals left by the previous trees. It's essentially the model learning from its mistakes iteratively, which makes it incredibly powerful for high-stakes regression and classification problems.
And a core business application.
Estimating customer lifetime value, or CLTV, in a customer data platform. The model takes a massive amount of historical demographics and purchase history and predicts the expected total future value of the customer, which is critical for guiding major strategic resource allocation decisions.
That covers the traditional supervised models. But as we saw in part 1, modern CRM systems rely heavily on complex, unstructured data like audio, video, and conversational transcripts. We need specialized deep learning architectures to handle that.
We do. And while the source material focuses on the traditional toolbox, it's really important to introduce the specialized tools that make multimodal AI possible. These models fall under the umbrella of deep learning, which uses neural networks with many hidden layers.
Okay, let's start with the tools that handle sequential, time-based data, like conversations or sensor readings. Recurrent neural networks, RNNs, and their specialized cousin, long short-term memory networks, LSTMs.
RNNs are unique because they have a memory. Unlike a standard neural network that treats every input independently, an RNN uses the output of a previous step as input for the next. This makes it perfect for sequential data like predicting the next word in a sentence or processing a stream of customer sensor data.
But they have a weakness.
Right. Basic RNNs often suffer from what's called a vanishing gradient, which means they forget information from the beginning of a long sequence.
And that's where LSTMs step in, solving the memory problem.
Exactly. LSTMs are a specialized type of RNN designed to explicitly remember long-term dependencies. They use complex internal mechanisms called gates to selectively remember or forget information over long periods.
So I'm talking to a chatbot.
If you've ever wondered why a chatbot can recall the context of a complaint you mentioned 3 days ago, it's likely powered by an LSTM. In CRM, they are vital for analyzing IoT sensor data streams to predict machine failure, or for powering chatbots that can sustain long, contextual conversations without losing the thread.
And for dealing with visual data, we turn to convolutional neural networks, CNNs.
CNNs are the workhorses of computer vision. They are specifically structured to process grid-like data, such as images or video frames.
How do they do that?
They do this by applying filters, called convolutional kernels, to the input data to identify features like edges, corners, and textures. In our B2C example, when a customer uploads a photo of a damaged product, the CNN automatically analyzes that image, recognizes the specific product model, locates the damage, and assesses its severity,
Which allows the system to trigger a contextual and accurate response immediately.
moving far beyond text-based support.
That significantly expands our supervised toolkit. Now let's look at the toolbox for unsupervised learning, the algorithms that discover patterns and structure.
Okay, we'll start with an algorithm that is excellent for understanding relationships. K-nearest neighbors, or KNN.
So KNN determines classification based on the proximity of data points. It acts like a social sorter.
Yes, KNN is highly effective for similarity matching. When a new data point comes in, say, a new lead, the algorithm looks at the K number of its closest neighbors in the data space.
And if its neighbors are good.
If those 5 nearest neighbors were all converted customers, the new lead is classified as high probability. In sales, KNN is a great tool for lead scoring. The model predicts the conversion probability of a new lead based on similarity to past successful leads industry, company size, website pages visited. It's based purely on who they are neighbors with.
Next, the definitive unsupervised method for segmentation. K-means clustering.
K-means groups similar data points into distinct, separate clusters. The goal is to minimize the distance between points within a cluster and maximize the distance between clusters.
And in a service CRM.
In a service CRM, K-means is used to identify customer support needs. It might segment customers based on ticket details and product usage into clusters like high-frequency, low-urgency technical questions versus infrequent, high-impact outage issues. This precise segmentation allows the company to tailor service experiences and staffing levels for each distinct group.
And finally, handling the inevitable complexity of modern datasets, principal component analysis, or PCA. This is the solution for when we have too much information.
That's precisely right. PCA is a crucial dimensionality reduction technique. This is necessary because modern data is often high-dimensional.
Meaning it has a lot of features.
A lot. Consider a product catalog. A single item might have 200 descriptive features: category, size, material composition, manufacturing specs, vendor location, 20 different prices. Feeding all 200 features directly into a recommendation algorithm is computationally slow and can lead to less accurate results because the noise outweighs the signal.
So what does PCA do to fix that?
PCA finds the essential structure, the principal components, which are linear combinations of the original features that capture the maximum amount of variation in the data. It allows you to reduce those 200 features down to perhaps 10 or 15 composite features that still describe 95% of the product's identity.
And how is that useful in CX?
In recommendation systems, simplifying vast e-commerce product feature data into this reduced representation allows for a much more efficient and accurate calculation of product similarity. It makes the system faster, the recommendations better, and allows other algorithms like SVMs or random forest to work more efficiently without being overwhelmed by unnecessary data noise.
That toolbox provides the classic foundation of AI, covering both prediction and discovery. But the field is rapidly changing. In Part 4, we need to discuss the next frontier, specifically generative AI, and the mission-critical infrastructure necessary to deploy and manage these sophisticated models responsibly.
Generative AI is arguably the most transformative technology in CX right now. It is focused on creating entirely new data, text, images, code that closely resembles existing data.
So it's moving beyond merely analyzing the past to actively creating future interactions and content.
Right. It moves AI from intelligence to creation.
What are the primary, most impactful applications we see emerging in CRM and CX?
I'd say there are 4 major impacts defining this space right now. First is the incredible leap in personalized content generation.
So we're talking about marketing copy.
Think automatically generated marketing emails, social media posts, or even personalized landing page copy, all tailored to the individual customer's preferred tone, language, and historical interest areas. That significantly improves engagement rates.
Second is the evolution of the virtual assistant.
This is the rise of chatbots with a human touch. Generative AI moves chatbots beyond scripted responses and simple decision trees.
How?
LLMs enable them to handle incredibly nuanced conversations, understand ambiguous requests, and generate fluid, human-quality text answers that sound natural and empathetic. They are becoming true digital agents.
Third, it augments the recommendation process in a very creative way.
It creates new value through product customization and recommendation augmentation. For high-involvement purchases like fashion furniture or complex B2B systems, generative AI can suggest novel product combinations or customizations based on a customer's taste profile.
So they can visualize things that don't even exist yet.
Exactly. They can see new configurations that the company hasn't explicitly designed.
And finally, it helps solve the age-old problem of not having enough data.
Yes, through data augmentation. Generative AI can create synthetic customer data that perfectly mirrors the statistical distributions and patterns of real customer interactions.
And that synthetic data can be used for what?
It can be used to train AI models more robustly, especially when real-world data is scarce, or when specific sensitive events like rare, fraudulent activities don't have enough examples for the model to learn from.
To properly leverage this, we have to master some new terminology, specifically around large language models. Let's do a jargon deep dive into LLMs and prompt engineering.
Right. Large language models, or LLMs, are the foundational models. They're vast neural networks trained on huge amounts of text, capable of generating human-like language, and they form the base of these generative applications.
And the critical skill for business success is prompt engineering.
Prompt engineering is the art and science of refining the inputs, the prompts, that you give to the model to obtain the precise, desired output and tone for a customer interaction.
And the training approaches are unique, often relying on the sheer knowledge base of the LLM. We see the term zero-shot prompting. What's that?
Zero-shot prompting refers to the model performing a task without any explicit training examples for that specific task. It relies purely on its general, pre-trained knowledge. A virtual assistant, trained on general product catalogs, can instantly answer a customer's question about a brand new product detail the day it launches, even though it hasn't been fine-tuned on that specific detail yet. It uses its generalized knowledge to provide accurate information.
And its cousin, few-shot prompting.
Few-shot prompting allows the model to learn a new task by simply providing it with a few of high-quality examples of input-output pairs.
How is that used in customer service?
A generative model, initially trained, generally can quickly adapt its tone to a new market segment, say, shifting from formal BDB language to casual Gen Z language by being shown just 5 or 6 examples of successful, desired interactions. This allows for rapid adaptation to new customer scenarios without extensive retraining.
Powerful tools require accountability, especially when they're creating content that represents the brand. This brings us to the operational side. It's not enough to build a great model. You have to run and manage it in the real world continuously. We need to discuss AI ops and LLM ops.
This is the infrastructure layer, the business continuity plan for AI. We're moving beyond traditional ML ops to AI ops, which encompasses the governance of all AI models, and LLM ops, which specializes in managing the complexities of large language models.
So it's about automating and streamlining the entire model lifecycle to ensure business success and reliability.
That's it.
What are the crucial concepts for businesses to understand here that ensure stability?
First, model versioning and governance. Because these models are constantly being updated, you must meticulously track every single change. This requires robust testing and approval processes.
And a way to go back if something breaks.
And critically, solid rollback procedures in case a new version unexpectedly introduces bias or reduces accuracy. Minimizing disruption to the customer experience is paramount.
Second is constant performance management and, crucially, understanding why the machine makes a decision.
That's model monitoring and explainability, or XAI. You have to continuously track the model's performance in production, its accuracy, latency, resource consumption.
And the XAI part.
XAI is vital because it addresses the black box problem. It helps you understand why the model made a decision. For a lead scoring model using gradient boosting, XAI shows precisely which factors, time on website, budget size, or industry vertical, were prioritized. This allows human managers to validate the model's logic.
For seamless and rapid updates, we rely on standard development practices being applied to the AI layer.
Right, continuous integration, continuous delivery, or CI/CD. This automates the integration of code changes and the deployment of new models. This ensures minimal downtime and guarantees that customer service agents or chatbots always have access to the latest, most accurate model version.
And to address the mandates around fair outcomes.
Bias detection. You must actively identify and mitigate bias in training data. If an AI model is used for sensitive decisions, like determining eligibility for premium service tiers or loan approvals, governance must ensure it doesn't show bias based on demographic indicators.
And finally, the fight against real-world degradation.
That's model drift. This is the gradual degradation of performance over time because the real world changes. Customer behavior shifts, economic conditions change, or, particularly in fraud detection, adversaries change their tactics.
So a model trained last year might be useless this year.
It might become completely ineffective. Continuous monitoring and automated retraining are essential to maintain the model's long-term effectiveness and prevent performance from silently collapsing.
That's a huge amount of technical knowledge to absorb. It shows AI is truly a vast, complex toolbox, not a single hammer. Now, let's tie all these concepts together in Part 5 by walking through 3 hypothetical real-world transformations, focusing on how different algorithms combine strategically to solve complex business challenges.
Yeah, we need to see how these individual tools, supervised, unsupervised, deep learning, are combined into a single cohesive ecosystem to achieve a strategic goal.
Our first stop is a B2B case study, a global manufacturer of industrial automation. This company deals with enormous sales cycles, custom-engineered products, and extremely long-term client relationships that hinge on reliability.
Their challenges were acute. They needed accurate demand forecasting months in advance, supply chain optimization to minimize capital lockup, and, most importantly, proactive churn mitigation for high-value key accounts where failure could mean millions in lost revenue.
Tell us about the AI ecosystem they built for forecasting and supply chain management.
They needed high accuracy because their inputs were so volatile. For forecasting and supply chain, they combined the stable, interpretable predictions of linear regression to set the long-term baseline trend.
Okay.
But they paired that with high-powered gradient boosting models to capture the seasonality, complexity, and noise inherent in industrial demand forecasting. This combination provided both speed and high predictive accuracy.
And then they paired that with what?
They paired that with decision trees and, crucially, reinforcement learning algorithms to optimize logistics and inventory planning.
Wait, reinforcement learning is an interesting choice here. How does that work in logistics?
Reinforcement learning is all about trial and error in a simulated environment. The algorithm learns the best logistical strategies, when to hold inventory, which shipping route to use, when to trigger a production run by receiving rewards.
Like a successful on-time delivery.
Right, or cost savings. Or it receives penalties, like delays or holding too much expensive inventory. Over thousands of simulated runs, it autonomously optimizes the supply chain strategy, leading to self-improving efficiency.
And for customer care, which is vital in B2B where machines are often connected to the internet.
They integrated advanced deep learning networks for predictive maintenance. Recurrent neural networks, RNNs, and long short-term memory networks, LSTMs, analyze continuous IoT sensor data vibration, temperature, pressure flowing from installed equipment.
So the LSTMs acted like a vigilant watchman.
Exactly. Because they're so good at processing sequential data, they could predict potential equipment failures hours or even days before they occurred, enabling the company to dispatch a technician proactively.
And finally, managing those complex account relationships and configuration data.
They used unsupervised learning for insight generation. K-means clustering segmented their complex customers based on product configurations and usage patterns, while PCA was used beforehand to simplify the vast amount of machine performance data into core components, making the clustering more efficient and meaningful.
The result was a significant competitive edge. Minimized delays, optimized production planning, and the transformation of their service offering from reactive repair to proactive maintenance.
Next, let's look at a B2C case study, an automotive retail leader. Here, the challenge shifts to high-volume personalization, multi-channel feedback analysis, and highly intelligent service for millions of customers.
Their main hurdles were achieving consistent personalization across the customer's entire journey, analyzing the widely scattered sentiment across all channels, and overcoming customer service bottlenecks caused by simple, repeatable issues.
Their AI ecosystem was designed for mass personalization and responsiveness. They used k-means clustering as the initial foundational step to group customers by driving behaviors, maintenance history, and preferences for targeted, highly relevant marketing campaigns.
To understand the voice of the customer, from all those channels, reviews, social media, surveys, they employed cutting-edge language models.
They leveraged transformer models and powerful NLP to analyze raw text data for proactive sentiment analysis. This allowed them to quickly identify pain points related to specific car models or service centers, prioritize issues, and gauge public reaction to new product announcements almost instantly.
And for service automation, they relied heavily on deep learning techniques to handle fluid conversation and complex visual input.
LSTM networks powered intelligent chatbots and virtual assistants, enabling highly natural and contextual interactions that could handle complex, sequential conversations about maintenance schedules or financing terms.
And the visual part.
They use convolutional neural networks, CNNs, to analyze both connected vehicle diagnostic data and customer-uploaded images, visual data of dents or scuffs, to automatically predict the required maintenance labor hours and parts. That led to faster, more accurate service quotes.
The outcome here was a drastic boost in customer retention and satisfaction, driven by highly personalized marketing and proactive issue resolution that felt seamless across all channels.
Finally, let's examine a retail case study, an online fashion boutique. This is pure personalization at massive scale, with a vast and constantly changing product catalog, the classic recommendation problem.
Their main challenge was simply achieving personalization at scale, accurately predicting preferences, and optimizing relevant product recommendations and website content constantly.
Their recommendation engine was a sophisticated powerhouse combination of supervised algorithms. They use linear regression to predict future purchases or average order value based on stable customer attributes like age and history.
And then for the core recommendation.
For the core recommendation and product classification, they employed a combination of logistic regression, support vector machines, SVMs, and decision trees.
Why use all three classification models?
They operate at different levels of complexity and robustness. Logistic regression handled simple binary decisions, like, will this customer click on this ad?
Right.
While SVMs and decision trees classified the complex products themselves based on detailed features, ensuring highly relevant suggestions, such as recommending a jacket that is visually and materially similar to one they just purchased, but in a complementary color.
And they extended that personalization beyond the product list itself to the entire site experience.
Exactly. They utilized random forest to personalize the entire website experience, including which layout, which promotional banners, and which categories were shown first to maximize customer engagement based on their predicted behavior. They also employed k-means clustering for foundational segmentation and PCA to simplify their vast product feature data, ensuring those thousands of hourly recommendations were calculated efficiently and accurately.
The results were tangible. Significant increases in customer engagement and conversion rates through truly tailored shopping experiences that made the customer feel understood. So what does this all mean? Our deep dive reveals that AI and CRM CX is not one giant monolithic technology, but a specific toolbox of highly specialized algorithms, supervised for prediction, unsupervised for discovery, deep learning for sequential and visual data, and generative for creation, each strategically tailored to solve a precise business problem.
From predicting churn to designing the next perfect product recommendation.
Exactly.
And it means you can move past the buzzwords and appreciate the granularity of the strategy, understanding that linear regression forecasts sales, while k-means segments customers, and LSTMs manage conversational memory. It allows you to appreciate why personalized experiences feel so tailored and how those core business insights are generated.
But the future requires more than just good models.
Right. It requires AI ops and XAI to ensure these powerful tools are trustworthy, transparent, accountable, and continuously effective as the underlying customer behavior inevitably changes.
That transparency and accountability are absolutely vital as AI becomes more and more integrated into core business strategy and starts making more autonomous decisions. And that leads to a truly provocative thought for you to consider. The source material discussed deep reinforcement learning, where the B2B CRM system acts as a sales strategy manager that continuously optimizes its approach based on client success rewards and penalties. This suggests a future where AI agents don't just recommend actions to humans,
but dynamically learn and execute entire profitable customer relationships autonomously.
Exactly. So the question for you is, what level of autonomy are you comfortable with in your future customer interactions? That's it for this deep dive. We'll talk to you next time.